We've been using the expression work is force times distance when the force and the distance are in the same direction. Let's take a look at what that looks like on a plot, or force versus position. So here we have a force versus position plot, and this of course only works if the force is constant. So I've drawn a constant force, and our object is moving from x initial to x final. And what we see is the work done is the area under that curve. Let's take a look now if we have a force that's not constant. How about something like this? If we're going from x initial to x final, and our force is increasing up to some maximum value, I have it increasing linearly, then the work done is the area under that curve. And it's a triangle in this case, so it's 1/2 F maximum delta x. And this is true in general. If you have a force that has some crazy shape to it, force versus position curve, and you're looking at the work done going from x initial to x final, it's the area under that curve. So in general, the work done can be written as an integral of the dot product of F and dr. It's how you're moving in relation to the force that's being applied, and we're looking at the area under that curve. If you're not in a calculus-based class, then don't worry about that. If you're in a calculus-based class, then you can take that and move forward and find the work done from various forces that are not constant. One force that is not constant is a spring force. So if we have a spring hanging here, and that's just the normal length of the spring, that's where it hangs if there's no weight on it, and we put a weight on the end, the spring is going to stretch. If we put twice the weight on there, the spring is going to stretch twice as much. Let's look at the free body diagram for the mass here, m. We have mg acting in the downward direction. We have the spring force acting in the upward direction, and it's not moving, right? If it comes to equilibrium, then those two forces have to be equal. And if we put twice as much weight on that, we have 2 mg in the downward direction, and we have the spring force up. So in this case, the spring force equals 2 mg. The way it works is the force from the spring is proportional to the displacement. And the proportionality constant is the spring constant k. If k is a small number, the spring is very easy to stretch. If k is a big number, it's hard to stretch. It takes a lot of force to get it to stretch a little bit. So k is the spring constant. Delta x is how much it's stretched or compressed. Some springs you can compress, some springs you can stretch, some springs you can do both. So that's the amount it is stretched or compressed from its equilibrium position. And oftentimes you'll see this equation with a minus sign here. I guess if you would write it as a vector equation, then we would put the minus sign there to show that if you stretch the spring, in this case down, then the spring force is in the opposite direction. It wants to go back to its unstretched length, so the spring force would be up. So that's where the minus sign tells you that If you stretch the spring, the force is in the opposite direction. If you compress the spring, the force is in the opposite direction. The force is always opposite the displacement. But normally what you care about is not this vector equation, because it's obvious when you look at a situation with a spring which direction the force is. So we just look at the magnitudes normally to find the magnitude of that force. That's a spring force. So let's take a look now at finding the work done by a spring. And if we plot our force versus displacement, you can see that this is a linear equation. F equals kx. Actually, usually it's plotted this way because it's a vector equation. We can look at this, find the area under the curve here, going from an initial position to a final position. And we've already said the work is the area under the curve. So in this case, that's a triangle. The work done by the spring is 1/2 kx squared, where x is the displacement from equilibrium position. If you want to use your integral to do this, if you want to do a little calculus, you can put in f equals kx. It's a simple integral, and you get 1/2 kx squared for the work done. I wanted to introduce potential energy terms. But first I have to talk about conservative and non-conservative forces. A conservative force ends up doing zero work along a closed path. Or another way of saying it is any path going from point A to point B gives the same amount of work done. So let's take a quick example here. If we're starting out at height A and we want to end up at height B, and we're in a gravitational field, we can move a mass from height A to height B, and we do a certain amount of work. The gravitational field does a certain amount of work. It's going to be mg times the height difference here. We'll call that h. In this first case, the work done is mgh. The force of gravity is down. The displacement is down. I'll call it delta y since we're moving up and down. And so we get mg delta y, or mgh, the distance between the point A and point B. Now let's take a different path. Let's go up and then down. And we can call this B. So for path 2, the work done by gravity, the ball is going up first. So I'm going to divide this into 3 parts. The first part is on the way up. Let me color code them. So I've got the red part, the blue part, and the green part. So let's do the red part, the work on the red line, plus the work for the blue, plus the work for the green section of the path, of the motion. So the work done on that initial part as it's going up is going to be mg, that's the force, times the distance, times the cosine of the angle between them, which gives us a -1, because the object is moving up, but the force of gravity is down. So we get this -1 there. It's doing negative work. It's slowing the particle down. It's slowing our object down as it moves up. In the blue path, the force is mg, the distance is b, but this time they're in the same direction. So it's doing positive work. It's increasing the energy of our object. The force of gravity is increasing the energy of our object. It's causing it to go faster and faster as it comes down. And then we've got mgh for the last part. So this is minus mgb, this is plus mgb. And we see that those first two terms just cancel out. Whatever happened on the way up gets reversed on the way back down, and when it gets back to where it started, it has the same energy, and then it falls the rest of the way. So the work done along path 1 was mgh, the work done along path 2 was mgh. It didn't matter. And it turns out, with the gravitational field, any path gives the same work. The definition here, the work done along any path between the same starting and ending points is the same. So that's what I've tried to show you here. Every time we started at height A, we ended at height B. We started in the same place. Case 1, case 2, case 3, case 4. We always started at the same place. We always ended at the same place. But we took different paths. The work done along path 1 was the same as the work done along path 2, was the same as the work done along path 3, same as path 4, the same as any other path we could have chosen. So that's the definition of a conservative force. Another definition is that going along a closed path. In other words, we start at A, and instead of going to B, we end up back where we started. That's a closed path. And that the work done along any closed path is 0. So we start and end in the same place. And those two definitions are identical. Pick whichever one you like. They're saying the same thing. So what's so special about a conservative force? Oh, first of all, before we start talking about what's so special about conservative forces, let's talk about what is not a conservative force. Let's think about friction. If we move an object and we slide it this way, and then we slide it back to the starting point, what do you think the work done by friction will be? As it moves from the starting point to the midway point, the work done by friction is going to equal the force of friction multiplied by the distance multiplied by the cosine of 180 degrees, because the friction force is opposite the direction of motion. And going from 2 to 1, the work done by friction is going to be the force of friction times the displacement times the cosine of 180 degrees. And we add those two together, and we do not get 0. Because it's negative all the time. It's negative on the way out, it's negative on the way back. You add them together, you do not get 0. This is a non-conservative force. So friction, air resistance, good examples of non-conservative forces. What forces do we know of right now that are conservative? Gravity and the spring force. And what's so special about conservative forces? Because they only depend on the endpoints. In other words, the work done along any path going from point A to point B is the same. So we don't really care what path we take. All we care about are the endpoints. Because of that, we can sort of come up with a special term that tells us what the work done is based only on the endpoints. So we don't have to worry about what path was taken and calculate the work done over the path. And we call that special term potential energy. So what's special about a conservative force is that when we integrate it to find the work done, we end up with a term minus another term. The first term, because we're evaluating it from x initial to x final. And we call this first term the initial potential energy, and the second term the final potential energy. Since we always use the term delta to be final minus initial, and this is initial minus final, this is negative delta U. So as an example, if the force was mg and we were lifting something in a gravitational field, we would get mgy, and we would call this term the gravitational potential energy, and we say the work done by gravity is negative delta U gravity. The potential energy term for gravity is determined from finding the work done by the force of gravity. If we are doing the work done by a spring force, we end up with 1/2 k x initial squared minus 1/2 k x final squared. We call this term the potential energy for a spring, and so we get this work done by a spring is negative delta U for a spring. So that's how we come up with these terms. So what do we know about now? We know gravity is a conservative force, so we come up with a potential energy term for gravity. We know the spring force is a conservative force, so we come up with a potential energy term for the spring force. And that's it this quarter. Next quarter, when you're studying electricity and magnetism, you'll see the electric force is also a conservative force, and you'll come up with a potential energy term from the work done by the electric force.